Today's lesson is how to find volume. Well, first of all, it would help to know what volume is if we're going to have to find it. So say that Tyler was helping me to clean up a mess that I had made, which is altogether likely in my case, since I am a klutz, of course. And so say that I had a bunch of 1 inch by 1 inch cubes or blocks, and I had spilled them everywhere, as I am likely to do. And Tyler got a bin, a plastic bin, and he was going to help put those cubes back in the bin for me, where they probably should have been in the first place, so that I didn't spill them everywhere. So volume would be the amount of cubes that would fit in that plastic bin. In this story, they happened to be 1 inch by 1 inch cubes, but they could be 1 foot by 1 foot cubes or 1 centimeter by 1 centimeter cubes. They really could be any size. So depending on the unit, it could be different. So the units would be cubic units. The amount of cubic units that can fit inside a container. We should probably get a drawing of this situation to model it as well so that we can remember what cubic units are. Aw, wah, wah. I will use my burly muscles to help pick those up for you. This contains all the cubes. And Mrs. Talestai was so happy. Yay! Don't worry, you don't have to draw all of that. But we should draw a container with cubic units in it. So I'm not sure if anyone's ever taught you how to draw a rectangular prism before, but that would be like a box shape. You can start with a rectangle, and then you draw another rectangle overlapping it. You can erase any parts that you might need to. Then we basically connect the corners to each other. Now this can be still a little bit misleading as to what's on the inside and what's on the outside. So if you don't want it to be a transparent cube where you can see all of the edges, now you can go back and you can erase the ones that would not be able to be seen unless it was a transparent or translucent container. So there you go. You've drawn a rectangular prism. So please label it rectangular prism in your notes. And when we're talking about how much can fit into that container, we're talking about other three-dimensional or solid objects as well, cubes, just like the ones Tyler picked up. So we'll draw ourselves some cubic units. Just can kind of see how we can make it look like it has cubes in it. And of course it's the magic whiteboard. They're perfect cubes. So now it looks like the container is filled with all of those blue cubes. So in order to figure out how many blue cubes fit in there, we could count them up, but we can't see all of them. Well, another way is to figure out how many cubes are in one layer and then figure out how many layers there are. So let's see if we can count all of those cubes. On the top layer, the one that we can see all of, we've got 1, 2, 3, 4, 5. And it's 5 by 1, 2, 3. So a shortcut would be 5 times 3 is 15. We can double check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So one layer, 3 by 5, would be 15. And if we're talking about a rectangular prism or a box, we know that it'll have the same number of layers on the top as the bottom. So our bottom layer would also have 15. We could add those up together and figure out that our total volume would be 15 plus 15 is 30 cubic units. But is it going to be reasonable to count blocks every time we want to calculate the volume? What if it was a huge container, like a swimming pool or something? You really want to count how many blocks are going to fit in a swimming pool? There must be a shortcut. And luckily for us, yes, there is. Basically, what we did is we figured out the length of the container and the width of the container. And then when we added the 15 and 15, it's kind of like 15 times 2 or doubled because there are 2 layers. So that would be the height of the container is 2 blocks high, 5 blocks long, 3 blocks wide. We basically multiplied 5 times 3 times 2. Length times width times height. Or V equals L times W times H. Remember, because of the commutative property, you can flip-flop the order of these factors. You could do length times height first if that was more friendly for you, and then multiply the width. You can always use the commutative properties and associative properties to decide what you want to do first. All right, let's get a different shape of rectangular prism. Let's make a tall one this time. Let's say that the height of this particular container was 7 feet tall. It's a container that a band uses to put all of its equipment in it, so it's really big. And let's say this container is 4 feet long and 2 feet wide. We could also say 2 feet deep, either way. So the shortcut would be volume equals length times width times height. I could do 4 times 2 and then times 7. I could do 2 times 7, which is 14, and then multiply that by 4. Ooh, that's kind of unfriendly. Maybe I'll stick with the order that it's in. 4 times 2 is 8. 8 times 7, 56, because 5, 6, 7, 8. And now what about the unit? We could say cubic units, but that's just if our measurement is unknown. Here, we know we're working with feet. But we multiplied feet times feet times feet. 3 dimensions in a 3D figure. So that means it's going to be cubic feet, or feet cubed. And since it's feet times feet times feet, we'll use a 3 as an exponent. Remember that that 3 exponent is because we multiplied feet times feet times feet. 3 different ways that we multiplied those together. So that's where our exponent comes from. Other ways of writing 56 feet cubed would be 56 cubic feet, or 56 q-ft. Looks like cuffed, but that's the abbreviation for cubic and the abbreviation for feet. Your task tonight is actually not to solve any problems, but to ponder the following. The formula we used today for volume was length times width times height. But sometimes mathematicians will use the formula the base area times the height is what gets the volume. How is, and this is just for you to think about, and you can jot down notes if you are like, oh, I know what to say in my discussion group tomorrow, but think about it, ponder it, and you'll be discussing it. How is length times width times height the same as finding the base area times the height? The base area meaning the bottom layer of cubes, the base area times the height. How is that related? how did we get height and height the same, but length times width here and base area here? Why do both formulas work? That's the first thing you'll be discussing in your discussion groups tomorrow.